add up 3 different motors. Now we're going to look at the line totals, and we're going to find the true power and the apparent power. And our first motor is a 25 horsepower motor. It has a true power of 18,650 watts and an apparent power of 27,089. That means it has a phase angle of 46.49 degrees. And we're going to find the VARs by taking the sine of 46.49 degrees and multiplying that times the hypotenuse of 27,089 to find our VARs over here of 19,644 VARs. Then we're going to look at our next motor, and it's a 30 horsepower motor, and it's going to develop 22,380 watts of power, but it's going to take in 31,869.7 VAs to create that power. And that tells us that it's got a 45.39 degree phase angle. You notice all these have slightly different phase angles. Now, that means we're going to take the sine of 45.39 degrees and multiply that times the hypotenuse, which is 31,869.7, and it's going to give us 22,688 VARs. Right there it is. Now, we're going to go to our last motor. Our last motor is a 50 horsepower motor, and it's going to develop 37,300 watts of cranking power, but it's going to take in 51,788.3 VAs of power to do it. That means it's got a 43.9 degree phase angle. Now, why do we want to add these up? Because as you connect these to a motor block control center, you want to know what is your total VA input, because that's what you're paying for, right? So before we do any power factor correcting, we need to find out what is this thing really going to take in. Can we add up are any of these things easy to add up? Or do they all add up? The only thing that adds up is true power and VARs. Apparent power does not add up directly. So what we're going to do is we're going to have a new triangle that is the whole motor block. And it's got a total amount of power of 37,300 plus 22,380 plus 18,650. All right, you can see that if we add up all the true power, 78,330 watts, we have 78,244 VAs pouring in to make that power. And so that means it's almost a 45 degree angle, 44.96. And what is the cosine of 44.968? About 70%. That's very inefficient, right? Pretty inefficient. So if we go back, we can look at this now and say, okay, if this is true, what is our hypotenuse? Okay, how do we do that? We know the tangent of this thing, right? Okay, actually we know the angle. Okay, so we can say, let's say that we want to use the cosine. The cosine of this thing of 44.968 degrees is what? 0.7. Almost 0.707, almost a 45 degree angle, right? Okay, that's the cosine of theta is equal to A over H, right? And we kind of like to know H. So 0.707 is A over H. I didn't plug in our A as I was supposed to, sorry. And so that is 78,330. Now we're going to exchange these two things. So we're going to take 78,330 and divide by 0.707. We know that's equal to H. So 78,330 divided by 0.707 gives us a total apparent power of 110 what?
714.5.
So you're pouring in 110,714 VAs to get 78. That doesn't sound like a fair deal to me. But this is our apparent power for the whole motor block. Okay? So if we corrected one or two of these motors, we could see what might happen. Also, what we could do is we could use a synchronous motor for one of them. If one of them is going to run all the time, or maybe two of them are going to run all the time, maybe we would want to make one of the motors, like the middle one, a synchronous motor, because it has a if it's overdriven, it can create a capacitive reactance instead of an inductive reactance, meaning that motor could become negative VARs for the whole block. And we need to look at how that would affect everything. But let's stop now. Oh, it took 6 minutes. Wow.